welcome again to Environmental Geology. This is Lecture 12, the second to the last of the series that we've got going. And in the past two lectures, we've focused on water-type issues, from water as a resource to water-related things with waste disposal. Today we're going to focus on water pollution and just a little bit on environmental law. And in that environmental law, I'm going to just focus on water alone, not so much on minerals and other issues with that. So there's going to be a lot of note-taking today, and so kind of get ready. I'll do my best to kind of go slow at times so you can keep up with the note-taking and writing. You'll want to focus your reading on chapters 16 and 18 in the Primus text, which of course is from Montgomery's Environmental Geology textbook. So water pollution, main topic today. And what is water that's polluted? Well, it's simply polluted directly or indirectly by human activity. That's us, folks. Things that we've done, and we'll focus on these issues today, ways in which we have polluted our surface and groundwaters. So water that is polluted directly or indirectly by human activity. And so this is kind of the main topic of chapter 16 in Montgomery's text. Now this water I'm referring to is surface water, lakes, streams, ponds, and of course the oceans. And that water we looked at earlier, the groundwater system. Now the main thing that happens, the main thing that we'll focus on will be chemical changes, chemical alterations that have been made by us to these waters. We'll go into some very specific details on some of them. But we've also affected the temperature in some places, and we'll mention that briefly as we go through it. So chemistry is the main change. Temperature is part of it, whether we're changing surface water conditions or groundwater conditions. Now here's a map from your text on surface water pollution in the United States, and you'll again, I'm not going to make you memorize from this map specific types. I'll go through a list of that later on some issues to remember. But if you look at the map, it's quite simple that roughly the eastern half of the United States, kind of the Mississippi and west, that ballpark has most of the surface water pollution. Now if we compare that, again, similar types of pollution, in terms of the groundwater now, you'll see it's kind of a mixed bag. There's a concentration a little bit in the mid-continent to part of our west, not completely all the way out there, but these are the major zones of different types of groundwater pollution problems that we're dealing with. So whether it's surface water or whether it's the groundwater, there's a lot of things to look at, different ways that we want to be concerned about these kinds of waters. One feature we have to look at and understand has to do with these chemicals, particularly that get into these groundwater systems, is something called residence time. Okay, residence time. Now we can kind of define it a little bit. It's the time of how rapidly a chemical cycles through a reservoir. Now the reservoir, again, if it's surface water, can be the ocean, a lake, a river or pond, or it could be in the subsurface as well. Could be part of the groundwater system, an aquifer in particular. So it's a time of how rapidly these different chemicals pass through or cycle through these reservoirs that we want to define. Now if we look at natural chemicals that we have been, of course, in like geochemicals that have been here since the beginning of the earth, and how nature has cycled them themselves through the system, okay, the time of natural chemicals is more easily evaluated through these reservoirs than chemicals we've put in. It's much easier to, because we have a long-term history, some reference guides to evaluate these, where all of these new chemicals as humans that we've introduced into the environment, which we'll classify here as anthropogenic chemicals, okay, it's more easy to do natural chemicals than these natural ones, or the chemical ones we've made, the anthropogenic chemicals. The reason why is that we don't really, they're so new, they're so recent. We don't completely understand how their breakdown byproducts are, how nature reacts with them. We don't have a long history. We don't know much about the behavior of how these things work because we're making so many of them so quickly we can't find the time to evaluate them all. So that's the complexity that we're faced with, and I'll throw some numbers at you in a little bit of how many chemicals we're talking about. It's kind of scary. Okay? So you want to consider the two different kinds, the natural geochemicals or the anthropogenic chemicals, the ones that we have introduced. Now, I think it's obvious. You learned this probably all the way back in grade school about how food gets, or chemicals can get accumulated in the food chain. All right? Well, we'll call these bad chemicals toxins of different types. And in the cartoon from your text, they show this little blob here kind of on the left of the fish, kind of like maybe algae of some sort. And they will absorb certain chemicals that get into the sea, the lake, wherever, okay, a pond, a river. And then if something larger eats that in the food chain, and then a larger fish and so on, eventually the group at the top of the food chain are going to have the most concentrated types of toxic materials. And heavy metals are particularly involved in this. And of course, we have other things that we don't even know about that can get into that system. We haven't even evaluated yet. Of course, humans being at the top, you start thinking of where this is concentrated in things like the liver. I know the organ meats are always a concern from kidneys and livers and stuff that concentrate particularly certain kinds of heavy minerals. They're natural filtering systems in the food chain. They may get caught up in the fatty tissues of these animals as they move on up. And all kinds of problems arise from it that we're worried about, the concerns. They include, of course, cancers as being the biggest concern. There's other ailments, nervous disorders, stomach disorders. We could go on with those. Birth defects, deformities that can occur, and just good old pain that hurts. So a number of issues that bother us. And that's why, as an environmentally conscious, we want to figure out what can we do about this water pollution stuff that we've got. Well, where are the main sources for all this stuff? I'm talking about the water pollution, and this cartoon, again, from your text can kind of point out a number of possibilities from things within cities to industries to our landfills, where we might have ponds of water we'll call waste lagoons or basins, and good old agriculture. The crops we grow with the pesticides and herbicides that run off the surface. You can put salts on highway systems to get rid of the ice, and that'll run off. So there's lots of different ways in which we can put this stuff into our water system that's a problem. And they'll get into the surface waters or the groundwater. Whether we're, have waste injection wells we talked about before with waste disposal, this comes around again. So whether you're in the country or whether you're in the city, you have these issues to deal with. And you're going to live in one of those places. So if you purchase a ranch, a farm, a property in a town, whatever, a business, you're going to be involved in this scenario. So I'm going to go through a whole list of these situations one by one so you can write them down. All right? But I want you to write down this Latin phrase in the bottom right-hand corner called caveat emptor. This translates into what we call let the buyer beware. Let the buyer beware. That's you. And so you may purchase, like I said, some land or a situation. I don't know if you can pick that up in the bottom right-hand. C-A-V-E-A-T, caveat emptor, E-P-E-M-P-T-O-R. Let the buyer beware. And so you wind up having the responsibility of this polluted area. Now, I want to break these pollutions now into two styles that they go through in your textbook called point sources and non-point sources of water pollution. In this case, they're talking about a stream. And we can see where chemical spills occur. That could be on a road, a railroad, could be stuff washing off the farmland or a feedlot, could be our old surface dumps, could be our landfills, a variety of things. Of course, industry waste just pumping things directly into the water. So a whole list of these types, okay? So point and non-point. So let's take a more close look at these two types, point and non-point. A point source is real simple. It's where you have one readily identifiable spot where you can go up and say, see that sewer pipe, that outlet? Here's this effluent coming out of there. That's the spot. Or some industry, a mill of some sort. Whole list of these things where it's just one particular spot where you can identify this concentration of pollutant going into the water system. It spreads out as a plume in those surface waters or in those groundwaters, and that's what we have to contain and deal with. So point source. If it's a non-point source, it's simply referring to a type of pollution source that's really spread out over a wide area. It's more diffuse. So it could be a broad farmland region where different types of chemicals run off the surface. Or maybe a big mining district, a lot of coal mines in the Appalachians or in the West, or gold mines or silver mines that might be pretty broad in their character. You could have some mines that can be very small mines and be very localized that could become a point source. So we could look at this acid mine drainage problem. Or like I mentioned earlier, the road salts. They're all over the place. So point and non-point sources. Now if you find this pollution, identifying the source as a point or non-point isn't always that easy, because these things can mix and blend as they move into the surface waters and into the groundwater systems. Some are real readily obvious. If you can see the effluent coming out of something, you could take that water and test it and identify it right away. And depending upon maybe a non-point source, depends on what kind of pollution is, what these different chemicals are. As I said, there's a lot of them. So it's not always that easy, but once in a while, if you can identify a very specific chemical, sometimes the nicknames they give to these specific chemicals that you can use to ID a very specific source of pollution, they're nicknamed tag chemicals or fingerprint kind of chemicals, sometimes trace element type chemicals in the periodic chart, or maybe a series of 2 or 3 in assemblage that you know are breakdown products of a specific type of chemical. So there are tags out there or fingerprints. Sometimes we even try to maybe add a non-toxic chemical to a spot to see where things are moving, see if they'll attach to other toxic chemicals and then identify that non-toxic material. And unfortunately, there have been, when we look at this pollution, not everybody's trying to pollute on purpose. In the beginning, maybe we were very naive. Maybe it depends on where the naivety level occurred or began, in management down to the common person watching. But some people may intentionally try to hide their pollution because maybe they had to pay big bucks to get rid of it and they didn't want anybody to know about it. So, the Midnight Skulkers gang or 3 o'clock in the morning dumping stuff where they're not supposed to do that. You could probably add one more to this list when you think about it. And that's terrorists and terrorism. And now we got this homeland security thing that we're looking at. All right, so here's where I'll kind of slow down a little bit. Let's take a look at these types again and kind of list what was in that figure. Water pollution types. The first category I want to look at will be industrial pollution. Industrial pollution. And what I'll do first is list these styles, and I'll come back to it, maybe give you some specific examples of some chemicals or things that are lumped together as maybe an inorganic, organic. So under industrial pollution, there's a group of inorganic metals. These are pretty nasty materials. There's a whole new group of lots of different kinds of organic materials. Our carbon type synthetic materials that are used and produced in industrial situations, so organics. One of the byproducts of certain types of industries is heat, water that may not be recycled but is vented either into a lake, a stream, or an ocean, or maybe sometimes injected, but it's the thermal problem. And these are often associated with particularly power plants. Nuclear power plants, they don't recycle they don't dump the radioactive water, that's recycled. But the cooling waters that cycle through, sometimes that is spread out. All right, the second category would be agricultural pollution. And of course, in agriculture, we have to sometimes add things to the soil to help the crops grow. And so this list of fertilizers, the concentration of fertilizers can be a problem. And then the chemicals to help us get the plants to maturity, and be healthy and productive. A lot of different kinds of herbicides and pesticides. These includes a lot of inorganics and organics as well, synthetic materials that are problematic. Also another problem when you're, tilling the surface of the earth, you're fluffing it up and you get a good rain at the wrong time, you get a lot of runoff of silt and clay and mud. And so we have these sediment problems. They'll fill into streams, choke off the stream, so there's siltation or that type of thing. So sediment problems are associated with agricultural pollution. They can also be associated with other things too, can't they? Industrial things, construction, housing industry, building highways. That's why we see a lot more of these little barriers up along different types of construction sites to hold back the sediment. Little black, they're not really big, they're like mini dams to hold it back. They let it settle, it contains it, prevents it from going into the ponds and streams and lakes. All right, now here's one I'll slow down quite a bit on so you can get all these written down. Because here's a list of some of these, not all, but some of the nasty types of chemicals. First with industry, in the inorganic category. These particular heavy metals, most of them are heavy metals, arsenic, lead, mercury. If you perchance know their chemical symbol, you could write those down to speed it up if you wish to. Selenium, cadmium, and plutonium. These are pretty bad pollutants of the inorganic category. Now I've listed two others, chlorine, which is used in water treatment. Asbestos comes in a variety of needs and uses, that whether we're mining the asbestos or whether we're putting it in buildings. Now we're trying to rip it all out and bury it. Big Superfund problems. I put them in green, or kind of lesser problems than some of these others. Certainly plutonium is a big bad one. It's radioactive problems associated with this type of industry product. If we jump to the organics now in industry, those carbon-laden ones, I've got some abbreviated. DDT, a good old pesticide from way back when, has been banned in our country because of all of the problems associated with it in the food chain. It's still used in some other countries. PCBs, polychlorinated biphenyls. Another good one, atrazine. Some of these are all synthetic products. Atrazine, dioxin. In the plastics realm, you got vinyl chloride. Good old types of foam, rubber types of material associated. Mostly, plastics like vinyl chloride, that you inhale them, they're certainly carcinogenic problems with, breathing that as fumes. We're not 100% sure about some of the problems with that in groundwater systems, though, long-term effects. Another one we'll look at later on, MTBE. That's just the acronym for now. A kind of additive to gasoline fuels. Something called DNAPL. And I'll come back to that. Another interesting one called BTEX that's made the news lately. We'll look at some of these, particularly the latter ones, in a little more detail in a bit. So those are some of the nasty ones, most of which can be carcinogenic or very problematic as water pollutants, groundwater and surface waters. Oil spills, we hear a lot about, oil tankers particularly. The worry of oil pipelines being blown up. Look at what happened in the Middle East with all of the problems we had in the early 90s and up until now, from Kuwait to Iraq, with all of the burning of the oil and the oil being released into the environment. And ship bilges dumping their stuff into the oceans and lakes. Not only transporting or dumping those chemicals, those raw toxic sewages into our oceans and into our lakes, like the Great Lakes in particular, but there are other organisms that sometimes get spread around. If you're a fisherman, you always see signs from one lake to another about cleaning things off of your propeller in your boat so you don't transfer stuff and start changing the ecosystem from one body of water to another. All right, under agriculture, I'll just throw a few at you. The inorganics, in particular, the fertilizers like phosphates that we use quite a lot. And of course, lastly, organic, human, and animal waste. And we looked a little bit, of course, about human waste, the idea of treatment plants and so on. In our country, we're pretty good at it, but other places they're not. And of course, the animal waste particularly come from feedlots. There are things associated with these human and animal waste, just besides the organics with that, but it's also bacteria problems and parasites associated with these. Different kinds of interesting critters that some of you may remember from your biology classes. Let's see if this kicks in. This is a cartoon. It's not in your book. This is what is called a DNAPL, bottom left-hand corner. The acronym stands for dense, non-aqueous phase liquids. Dense, non-aqueous phase liquids. And here's this barrel, 55-gallon drum of DNAPL that got spilled accidentally, maybe intentionally. And of course, it sinks, it's denser than water. The boundary, the light green in the middle here, this is above the water table. The darker green is below the water table. And that stuff will sink all the way down until it hits an impermeable zone. Even in this impermeable zone, it'll want to leak and go through any kind of small porosity it might have, cracks and so on. But it kind of flushed around the side and came down and got concentrated at bedrock where it's impermeable. And so here's a water well. Well, this is pulling it right into that water well. DNAPL is a carcinogenic category. It's nasty stuff. We use it a lot in cleaners and dry cleaning. So here's another very specific example of one of the kinds of DNAPLs you might want to write down in big white print in the bottom, called perchloroethylene. Perchloroethylene. There's a number of different types of DNAPL materials. There are solvents, synthetic chemicals that we've made. In this cartoon, which is not in your text, here's a particular spill at the surface. You can see the water table boundary. This stuff sinks. Well, different kinds of DNAPLs, and you can imagine what an LNAPL is. Instead of a D, it's an L. So dense, D for dense, L for light. It's just, so gasoline, floats on water. So gasoline spills would float on the top. So think of this rainbow of all these different chemicals we got that accidentally get spilled into nature that will, the density contrast, they might just wind up maybe in the upper part of the water table. And it depends on how much salts are dissolved in that groundwater. And of course, those that go all the way down to the bottom. So these can be pretty nasty things. Here's LNAPL. That simply means light, non-aqueous phase liquids. And of course, DNAPL, as I mentioned, the nickname for perchloroethylene in the literature often is called PERC. Kind of an interesting kind of chemical. You do not have to write the chemical formula down here and worry about what kind of bonds there are in this structure, but because it's kind of got this tetragonal character, it's kind of hard to pull that apart. It doesn't dissolve too easily, so it stays solvent for a while. All right, here's another one of these things I mentioned you should write down. BTEX. BTEX is a group of chemicals that are represented by products when gasoline breaks down. If you have gasoline spills, whether they're at the surface or they're old gasoline tanks that were buried and they leaked into the groundwater system, they will break apart with time. And these byproducts can be really bad, very carcinogenic, very toxic to various parts of the food chain. So BTEX is the acronym for a couple of things. B for benzene, T for toluene. So benzene and toluene. You probably, if you're at a distant site, you're not going to be able to read these small chemicals at the top of the screen, but benzene, T for toluene. E stands for ethyl benzene. Ethyl is ETHYL in this case, ethyl benzene. And the X stands for xylene, XY. So a variety of these organics are in as byproducts that we need to target. Now just think, if you got a spill of something, and already the list is beginning to grow, they can break down. Well, what are their byproducts? Sometimes they break down, they become non-toxic. Sometimes they become other toxic chemicals, and they'll go to different levels, and so finding them, tagging them, targeting them, monitoring them, cleaning them up becomes a major, major challenge. So DNAPL, LNAPL. Let's go back to that LNAPL. LNAPL, gasoline would be an example of an LNAPL. It's light, will float on water. I've made just a few comments about MTB. You do not have to write all this down that you see on the screen. Okay? MTBE is an acronym for a gasoline additive. It's called methyl tertiary butyl ether. We add this to gasoline to help it burn better, to create a cleaner kind of air. But unfortunately, in a few places, since its use, it's been identified as a groundwater contaminant in a variety of aquifers. I know California was one of the big places. But there are a number of others I mentioned here just in this black and white about California and Texas and Maryland. It's around, and so now we're looking at this new chemical that we've tried to, we thought would be good to clean up the air, and it turns around and it may be very problematic. So right now the issues of argument are still on this one. Some people say it's really bad, and others say, no, it's okay, and where's your proof, where's your testing? You've got to test stuff, and it takes a long time to say, yes, that does that. I mean, take a look at all the arguments that went on in the cigarette industry over all the stuff that's in cigarette tobaccos and different kinds of smoke, secondhand smoke. Same thing here. It's a very complex situation. At least for you Kansans, I can make a general statement that Kansas has been really good in cleaning up and remediating the MTBE situation in this state. In fact, we're kind of leaders and have some of the best water supply treatment programs in the nation. This is not a figure from your book. I found this on this Delta Environmental website, and they've got these different states of where they're actually now actively cleaning up and working on these and how far they've gone in there. So, every time we see something, we jump on it really quick now. But no matter how quickly we can jump on stuff and do research, there's always something new around the bend, something new that's coming up. I'm not sure if you heard of something like this in biology classes, Cryptosporidium. Cryptosporidium is a type of parasite that's out there that's kind of new in our water systems. If you're into hiking and backpacking and getting out into nature, you'll want to watch for not only things like Cryptosporidium, but a whole bunch of other stuff. So let's go through this list of things related to water quality. I use this in my intro physical geology and intro to geology classes, and just kind of, it's good to come back and review some of these basics. We have standards on water quality. There are federal standards and state standards that are set, and they change. What they do is they look at chemicals that we've studied. We look at new chemicals, say what are the toxic levels in there, and we may classify something in parts per million, parts per billion, whatever, and say, okay, this is as much as you can put in. This is what we can tolerate, so we've got to clean it up to that point. So they set the standards. It's an ongoing, continuous, difficult process. And here's some things that you find in water. I think you could probably recognize it. You look at a vitamin pill bottle, okay? Sodium, calcium, chlorine, sulfate, bicarbonate, and iron. These things are fairly harmless in our waters compared to the next example list. Lead, selenium, chromium, arsenic, and mercury. We listed those already. They're pretty bad things to have in our water. We want to get it out. All these other pictures you see up here are a variety of different kinds of organisms. I'm not going to name them all. Some are very common. You might know some of them like E. coli, Escherichia coli. All of you have that in your intestinal systems. Okay? Giardia lamblia, something that was introduced to the United States or North America about 1971 around Aspen, Colorado, and spread all over the country in our water systems. If you're into backpacking, you should learn about how do you deal with this thing. Filter your waters. Chlorine tablets and iodine tablets don't kill everything. Boiling water is probably the best, and certain sterilization process, special filters, because some of these things go through that. Cryptosporidium is kind of new out there in that mess of things. And there's a bunch of other kind of nasty things up here in images I won't give you the names of, but there's a lot of it out there. And of course these things can be brought up and carried by other organisms, not just you drinking it and ingesting it. You could get it by a wood tick, a mosquito, and so on. So, and of course now the newest one, terrorist situations. Terrorists dumping things into our water supplies, into our lakes, our rivers, our community water supplies? What about organisms that could be bad, like, worse than this? All right. And I'm not going to make this long list of biological things, but they're out there. So it's part of this water quality. All right, here's some stats now I wanted to bring up about these chemicals and the difficulty we face in looking at this. In 1990, in the American Chemical Society journals, in 1990 they recorded the 10 millionth entry of things that have been identified in nature since 1957. Some of these are newly created chemicals by us, or they're simply things we've identified out there we didn't identify before this. Natural things. 10 million. In what, a 30-year period. A lot to think about. Well, we keep producing these quite rapidly in our laboratories, trying to come up with new things. They say there's roughly 100 new anthropogenic chemicals that we synthesize every year. 100 new ones. Right now, around 2004, it's roughly 66,000 anthropogenic chemicals have been produced. These are synthetic things we may use for pesticides, herbicides, trying to change things because organisms we're trying to kill maybe become, it doesn't work anymore. To wipe them out. Now, we take those 66,000 chemicals, we add in 100 a year, 90% have not been tested for toxicity. Only 2% of all those have what we call this complete rainbow, this complete screening thing for complete accuracy on what effects they have. See a lot of jobs for chemists here? Biologists, geologists. We could add a lot more to that list of people who are needed to help out. There may or may not be the money there sometimes too. That's the other problem. There's a need for the jobs, of whether or not they're going to be available because of what the funds are. Now there's some easy tests we can do on running on people for seeing if they have these toxic problems. Urine analysis, sweat swabs, saliva swabs. These are non-invasive techniques to get fluids to analyze the chemistry of things that can be signs that you have it in your body. They're not always 100% sure. You may have something trapped in other parts that these tests do not identify. So we've got these non-easy tests. We'll call them the hard tests. Blood analysis, removing pieces of fat, these invasive techniques. And of course they cost money. And a lot of people don't particularly like sometimes to go through these types of tests. Sometimes you may want to have them done on your own. I know this spring we're having our annual state of Kansas health test, and one of the processes is you can have blood tests taken and all different kinds of chemical analyses run on your blood for your health. And sometimes goofy things pop up in these analyses. And then more tests may be needed, but you have the choice to say yes or no, I guess. So let's give your hands a little bit of a rest here and look at a few pictures. Here would be an example of an outlet to a mine up in the mountains. You've got a gate over here. They got to notice it's locked off in a fence so people can't crawl back in there. But you got stuff draining out from underground in a mine, and that groundwater has a certain chemical quality to it. Some of it may be very, very toxic. It may be just acidic. For example, here we have the color stain here, this red and yellow. That's often common for iron stains. So maybe it's just an acid mine type of drainage where the acids are produced by waters draining through the mine and coming out. The pH has gone down a little bit. I threw acid rain in there because acid rain can also be produced, but it's not draining out of the ground. It's where it rains. So if you're pumping all kinds of pollutants into the atmosphere, like nitrogens and sulfurs, and you create sulfuric acid and nitric acids and so on, we have a lot of industry that does that. You have a lot of rain that's even more acidic to add to the more acidic groundwater, and you have even other problems. So that's acid rain. So there's two things on here, acid mine drainage and acid rain, types of kind of sources. Acid rain would be what? Non-point. Acid rain would be coming over a broad area. That'd be non-point source. acid mine drainage right there. That's your point source. All right, let's take a close look example right here in the city of Hays. This is the old Ellis County landfill. It was closed in the 90s. It's now, it's been leaking. Water is migrating through it and moving southward towards Big Creek. And as it did, this pollution plume occurred. And there were some people who lived in this area. They had their water wells there. All right, so the landfill is the point source. It was easily identified as the culprit. So Ellis County and the landowners came to an agreement, okay, to say, okay, you know, it was out of court settlement as to how much money would be exchanged and so on. And of course, also other things happened. Certain environmental firms came in, put in monitoring wells, and to see, well, is this going to continue and get worse and leach even further down towards Hays, or would it kind of stop or be reduced? Put some things on it. So what they did is they put a bunch of monitoring wells all around the southern edge of this, and to see what was happening to this leachate. We introduced that term earlier, the toxic material. And like I said, litigation is what they solved out of court. Well, they now know that the plume has receded a lot at this stage. And that's the last I've heard at this particular moment in time with these monitoring wells. So again, it's someone has to come out there and get involved to look at it. Another type of point source, feedlots. Feedlots are a major source of organic waste, okay? So, or food processing plants. You might want to write those two sources down on your notes. Feedlots and food processing plants, you know, turkeys, chickens, the list of animals we process can go on in terms of that, and that has some organic waste that can come out of those areas. But we know where they are, and usually then would be targeted as a point source type of pollutant. Here's a map from your text of non-point source pollution. All right. So I need to go back to that one. I go through that a little fast on this last one. Okay. You got feedlots and food processing plants would be considered point source types of pollutants for organic waste. Again, a map of non-point source. Here we have all of the different possibilities over this huge breadbasket of farmland and ranches, where we use particularly farmlands producing lots of, or inputting lots of fertilizers and nitrogen coming off from this. And of course, this spreads into our lakes and streams in these regions. I'm not going to pick on any particular state. This is always an unchanging thing. This is a 1987 map, so it's certainly either bigger or smaller in different areas across that thing. Now let's say a little bit about nitrates. Okay? Nitrates as a pollutant are mainly from non-point source runoff, as we saw in that previous figure, by the over-application of nitrogen fertilizers. Mainly from fertilizers. We get a little carried away, want to get that production up, to get everything we can out of the land, and anything that runs off winds up in the streams. Or from poorly or untreated sewage. We'll bring this nitrate material into our waters. So two kinds of non-point sources in here. The second one can be considered more point source if you know exactly, of course, where the sewage treatment plant is, or a feedlot, but poorly or untreated sewage. Or like in industry, you can have nitrate-containing waste that come out of certain industries, particularly paper companies or munitions plants, just to name a couple. There are others. So kind of non-agricultural sources here, okay? Paper mills, munition plants. And of course, since agriculture is kind of really has a lot of fingers pointed at them, farmers in rural communities are mostly threatened. They have a more daunting task. If we're going to try to clean this up, this concentrated nitrate problem, they seem to have had the most problems with it. because it is a non-points thing. It's spread out over such a big area. It's diffuse. It's been going on for a long time, and we continue to do it. We're trying to find techniques and ways to cut back on everything, the herbicides, the pesticides, the fertilizers, to make that work better for still a high yield out of that product. What happens if you get it in your body, though? Okay. What happens if you get nitrates in humans? What are some of the things that could be involved? Now, instead of maybe trying to write everything down that you see up there, sometimes you can take a look at the words in reds. I'm trying to emphasize some very specific parts of this. But as a health hazard, okay, particularly in infants, is where the nitrates can be a big problem. It happens to be a condition known as blue baby syndrome, okay? If they ingest too much fluids with nitrate concentration and get that into their system, they go through this. Or if the mother has that and concentrates in the fetus. Here's kind of what goes on a little bit, more biology, so to speak. And I'm not going to hold you to all the stuff that's up there on this, but basically, again, the red stuff would be what is going on quite specifically. But the nitrates converted in your gut, your stomach, intestines to nitrite, and that combines with blood or hemoglobin, and it forms something called methemoglobin. And what this does then is reduces the ability to absorb oxygen and carry oxygen, and that's not good. We need that to be transported, and you have less blood to the brain, you can have other problems. Now there's other things out there that can be called high nitrate, high percentage of nitrate. Notice it says may cause. The word may is a wonderful word, and it's always very useful. It says it could possibly, may, a lot of words like that in our vocabulary, but it may cause other health problems, such as cancers, teratogenic effects, which are things on the embryos. And so, you know, targeting a particular chemical to a very specific disease is not easy. Because there's a lot of things that sometimes can cause the same side effects, the same types of cancers. And in our natural world, we like to finger point. We want to say, this is causing it, and therefore I'm going to sue this individual. And you may or may not win because there's so many possibilities and what ifs. And just think of that whole list of chemicals we looked at, and the difficult task of having multiple sources coming in that tag upon one another or attach. And it's not an easy task. But nevertheless, we know we have problems. But we have all this stuff, don't we? We have all these things we want, all the things that we enjoy, and a lot of the byproducts of this are all these chemicals that get into our water system. So we have choices, but it's a difficult decision sometimes which way to go. Here's an obvious picture of sediment pollution in a stream. Over silted, that's going to block out sunlight, so photosynthesis may be reduced. You mess with that, you may change the chemical system in here, where if you start eating up the oxygen, this siltation can come from lots of sources. Again, construction sites, here it is filling up a sewer system. It comes out and, you know, there's a lot of silt and clay and mud in this thing, and we're always testing it. One of the tests of how deep light can penetrate is this little disc. If you've ever had some classes in limnology or lake studies or oceanography, this little black and white disc, you settle down in the water, and when you can't see it anymore, you measure a certain depth on a string or a cable, and that's how far the light penetrates. Well, organisms live in that upper zone, the photic zone, for photosynthesis, or phytoplankton, one of the beginning basic parts of the food chain. And so we want to have lots of ideas. So, you know, I've mentioned all the problems. We've got all the chemicals out there. Well, there's lots of different things we have to do to try to solve this. Here's a diagram out of your textbook, and I believe it didn't come out very good at all in your text because you've got a black and white one, and you can hardly see these red lines in there. It's the effects of wastewater and organic matter, and it could be and or organic matter, on dissolved oxygen in content. And this kind of goes along with what we call the biological oxygen demand of organisms in water. A certain amount of oxygen, we have more oxygen, a certain amount of oxygen, or too little oxygen. And so by dumping things into the streams, these graphs are kind of showing you what we refer to as an oxygen sag. Here we may have a single source downstream, and all of a sudden the oxygen percent goes way down. As we graph that, take a chemical analysis of the dissolved oxygen, that's going to have a major effect on the ecosystem right in that particular region. Notice this is distance downstream, or time. Downstream distance, which is relative to time, depends on how fast things are flowing in that stream. But that could be a few hundred feet to several miles. And so how that works out, but that's affecting that ecosystem in some fashion. Here we have two possible sources. Maybe they get dumped in one, then right downstream is another one. And so this stream's kind of getting a double whammy. Maybe that what's getting dumped in doesn't affect the BOD too much. But here we got two smaller sources that can then combine together and be a bigger problem. So how many industries you have along the stream? How many pipes you got going into it? Let's talk about that BOD a little bit more in case you are not sure what it means again. BOD is kind of a measurement of something, all right? It's a definition taken from your text, kind of shortened a wee bit. It's the amount of dissolved oxygen needed by aerobic organisms. Those are things that need oxygen to break down the organics, this wastewater that might get dumped into a stream, okay? The organics in a given volume at a certain temperature over a given time. So it's a very specific unit. I will not make you memorize any units, but to get a feel for what's happening, if you have a lot of waste in the water, you're going to change the BOD. You're going to reduce it. You're going to reduce the oxygen. There's going to be demand to eat up that organic. Not only that, when those organics get eaten up, the waste material, sometimes it becomes solids, sift to the bottom of the stream or the bottom of the pond and make that bottom of the pond more anaerobic, more reducing in its chemistry. So really, when you think about it, this stuff's been in nature anyway. This is a natural process, okay? But if we add more than what nature can take on its own in its usual fashion, we affect that process, and so we can speed things up. We can speed up the toxicity level of the water, we can speed up the chemical changes that take place, and we can dramatically change what it looks like, physically, biologically, and so on. So what are some of the variables that would affect BOD? Well, one is flow rate. The faster the flow rate of your particular stream, river, whatever, that's good in one way because it creates and adds more oxygen to water. So you have more oxygen available for nature to clean things up. So a fast flow rate is good. If it's just still and not moving, that's not good. That's kind of a stagnant condition. It can really speed it up and make that whole pond kind of turn pretty fast on you. Water temperature, warmer waters are not good. pH conditions, that depends on what's in there, but rapid changes in pH one way or the other has an effect on what it does to organisms. Too acidic or too basic, and we can have dramatic changes just in the organics that are in that water. Percent of pollutants. Obviously, the more pollution you put in, the worse it is. The more wastewater gets dumped in there. So here they're kind of looking at silt and checking the chemicals, trying to see if there's any plankton floating in there, what is the color, what's the transmittance of light. Here, of course, we see an effect of a major problem with BOD going wild. In this case, all the dead fish in this pond. And then once their remains sink to the bottom, which they can, we have a big problem. So here's kind of a thing related to that, all right? The idea of changing the chemistry and the biology of this body of water so that it begins to not appear clean and fresh, and you have lots and lots of of plankton and organics growing in it, a bloom. They called it an algal bloom. Back home we called it dog days. The green slime that would come on the lakes, and if the wind was right, it would blow it to the other side of the lake. If it's blowing your way, all this stuff is on your side of the lake. It stinks, it smells, changing the chemistry affects all of the other things in the water. And all this stuff here floating in Lake Tahoe is all this scum. Well, think of all the, the growth around Lake Tahoe. They grew quite rapidly. So by adding fertilizers to the water, the runoff into these bodies of water just causes that bloom to grow even better. You got a good garden going. You're speeding up a process of blooming called eutrophication. Okay? And this lake up here on the top, more your typical nice clear blue lake, although it could have pollutants in it, of other things. But here's this kind of more green looking slime, the biology building up. In some lakes where eutrophication has gone so bad that plants up the chain of evolution, okay, you might go from these algal things to more grasses, and then you might get lily pads, and they start choking it off. Next thing you know, any winds blow silt in, and you got yourself a peat bog. And it kind of, and you can speed that process up. Well, if this is a good old fishing hole, you want to clean it up. So we could add chemicals to this and try to kill these off. So it's a game. It's whether we, can do this. I know Canada and northern states in Wisconsin, Minnesota have a lot of things they deal with the development of all the fertilizers and the raw sewage, poorly designed, ways to just get rid of the waste, and then these lakes are getting eutrophied. Now, one way I know in northern Wisconsin they do is they lower the lake level on a reservoir. It's got a dam. They let everything freeze off. But it makes the lake look great. It's great for tourists to come up and see a pretty lake. But on the other hand, that if you go too far, you affect the food chain, and the fish don't come back as fast. So people run around speedboats, but not fishing as much. So anyway, that's kind of the story, a general overview of this water pollution problem. All right. What are some of the things we're doing to try to clean it up, to maybe abate these situations? Mitigation, okay, mitigation. Here's a list of techniques of some things we can try to do to clean up waters. One common way was to build a pond they call a settling pond. And so depending upon how you design it and the shape of it and where it is, kind of upslope from your stream or major lake, and then you let that stuff, the water, filter into it, okay, the sediments settle out, and then fresher water kind of can then leak out maybe the top end and go downstream further into your major river or stream. You're kind of using nature to filter itself. In this case, it's mostly sediment type of filtration, not so much chemical. Let's say you target a spot that's a point source pollution. Well, you get a backhoe or a great big dredger and you dig it out. Now you could dig it out of the bottom of a lake, along a shoreline, the ground surface itself, get the groundwater out, and you remove it. And if it's a certain kind of spill, maybe it's a gasoline spill, you spread it out, you let the gasoline evaporate. And then you could, if you wanted to, recycle that soil or that sand. Always, once in a blue moon, you might open up a bag of potted soil or gravel you bought somewhere at some garden center, and it's got reeks of gasoline. Well, they didn't let it dry out long enough. You find a lot of these sources of that. Or you can aerate it. Oxygen is good to help clean things up. We saw in water treatment, aeration is very, very good. And that helps push the biological things, cause chemical reactions to occur. Or you may want to try to physically isolate the plume. Put things in the ground to contain it. Grout. It's very costly to do something like this, to dig trenches and fill them in and keep that from leaking and permeating, moving away from a point source spot. Physically, isolation is tough. Chemical treatments of all kinds. Add one kind of chemical to break down another kind of toxic chemical to make it non-toxic. A lot of big lists there. Or use biology, bioremediation. Use organisms, certain types of bacteria will eat up hydrocarbon oil spills. A variety of communities, we can get things like in Hays, Kansas, we use these last two activated charcoal instruments or air strippers. again involving oxygen or filters that filter chemicals out. The last two, you can get the stuff out, but you still have stuff you've got to get rid of. Same thing with dredging. You can get it out and kind of clean it up in some fashion, but you got to get it out. So you can mix and blend a lot of these together sometimes. So that's the task of trying to, isolate the first, find the plume, monitor it, where's it going, and see if nature will take care of it, or dig it up and do the best you can to clean it out. Non-chemical bioremediation, okay? Let's talk about that a little bit more. Your text goes into this a little bit in detail. These are bacteria that eat organics. How we can use nature to directly or indirectly clean up this water pollution or prevent water pollution. That would be the indirect. Bacteria that eat organics. Here's one that's mentioned in your text, Bacillus thuringiensis. This particular thing will kill other insects that are harmful to plants, but these particular things are not harmful to humans, mammals, birds, or fish that we know of. Ladybugs, you probably heard about that, are good in your gardens. Okay, so there's a lot of other, that really the biology comes to play here, as does botany. That's the stuff we're growing. Larvae that prey on other insects could be used. A good example that's used in your text. And all these things they're preying on, of course, are things that are attacking our food sources. That way we wouldn't have to use insecticides to get rid of it. Here's another good one. Sterilized insects. And then you release these insects into the other insects of the same species, and then in the gene pool it becomes depleted because they all become sterilized, and then they can't survive. They don't produce enough offspring, or any. So, interesting game. Here's one that's interesting. Baiting insects with synthetic scents. Now, if the synthetic chemicals that use to create these different smells or scents that attract other insects and then bait them in some kind of a trap of some sort that kill them, okay, as long as those are non-toxic synthetic scents, fine. Otherwise, we've just added to the problem, haven't we? And lastly, this is, this kind of hope for a lot of things, I guess, in the realm of biology, is genetic engineering to create more resistant plants, which we've done, and we'll see where this brings us in the future. So for you biology majors out there, this is a tremendous area to look at in terms of food production, cleaning up the environment. See what you can invent in the future. Did I go through that too fast? Need to go back, anybody? Okay. Cartoons a little bit here. Here we have this idea of this downstream here is a major river off to the right, and so if you have runoff, you got sediment that'll settle into this pond, and then you can pipe off the water, that fresh water. Of course, what can that do? You can get silt coming off of here too, can't you? So you might want to put it directly into a stream. What could happen to this pond though in time? Fills up. And either dredge it out and dump it somewhere else, or you have to continually dredge it. So it's not a simple solution. It's just one possibility. Here's our good old landfill with a leachate plume coming out, probably a mixed bag of Dean apples coming down below the water table. The best thing to have to hope, to have these plumes move through are sand, particularly sewage-type pollutants, living things, the bacteria and sewage types of pollutants that can get into our water. Chemicals are a different story. Chemicals may not get as easily filtered. They may remain dissolved in the water. Now, I always tell my students when they're measuring rock layers to take a close look of what individual types of clays you might have. You may have kaolinites or illites or montmorillonite type clays in the ground. Certain clays will attract and absorb to their surfaces different kinds of chemicals. Some of these synthetics. Some do, some don't. And so knowing what your geology is important to understanding how the plumes move through that ground. So nature can do it, we can kind of help. Here's a map, a GIS kind of map of the city of Hayes. This big green area is our perk plume. It was identified from an old dry cleaner plant. One of Hayes' water wells was in this area. We shut it down. So what they're doing is they're taking this water down to an air stripper and an activated charcoal system, and they clean it up. Then that new clean water goes back up to the water treatment, becomes part of the Hayes' fresh water supply. So many cities are doing this. And today this plume has really shrunk. This is its maximum where it was at one time. It's much less than that now. Here's our activated charcoal, cleans it up a little bit. They take this water, move it over to the air stripper, cleans it completely, and then that cleaned water, 100% pure, is then put up to the water treatment plant. So we've been able to recycle and save this polluted water. And that's the games we do. Here's an example of one of our Fort Hays graduates going by an old gasoline station down on 8th and just east of Main Street. And what they're doing is putting in all these monitoring wells and pipes, and they periodically come back and check on a gasoline spill and other organics or organics associated with this old gasoline station, the oils and stuff like that dripped out and leaked through the concrete. And these things are being cleaned up. So we are doing things. We are mitigating. Here's one that's represented in your book about the California Gulch, which is located in Colorado. Okay, and what we're doing is taking remote sensing, taking a technology called Avarice. I think Avarice is in here. You can barely make it out if you're on a TV screen at home, but AVIRIS, Avarice, Airborne Visual Infrared Imaging System. Airborne Visual Infrared Imaging System. Plane, like U-2 type plane, flies over and takes hyperspectral pictures of the surface of the Earth. And all these different types of spectra can be identifying specific kinds of stuff. Agriculture uses it. We can look at different types of crops because of the spectra given off. In this case, we're looking at different kinds of toxic materials given off and say, these are the bad ones, let's fix them first. So GIS can be utilized to target and monitor and mitigate problems we have in the environment. Now you have a figure like this. It's not the same exact one, but it's very similar. It's California Gulch that's in your text. All right, take a little slight shake your hand. We're going to jump briefly now into a focus on environmental law, focusing on water, not minerals and other types of things that are in the chapter. Since we've been looking at water issues, I want to stay focused on water only. I want to introduce two broad types of environmental laws regarding water, both surface water and groundwater. So under this water rights list, you need to write down this very first doctrine. It's called the Riparian Doctrine. The Riparian Doctrine is a water law that states that the landowner who owns the land next to that body of water has the first right to use that water. Now this comes from England. This doctrine was brought over from England and massaged, so to speak, and tweaked and subtly changed, okay? But the landowner who has the land next to this body of water has the first right. However, we've tweaked it by saying, well, it's within reason, within reasonable use of this water. You don't get it all. Really, the states control it in this legal fashion, okay? But it's more involved with quality issues than it is in quantity issues of where we delegate this particular doctrine. We'll look at a map in just a bit. So Riparian Doctrine is the first doctrine. The landowner has the first rights. The second doctrine is called Prior Appropriation Doctrine. Now the holder, in this Prior Appropriation Doctrine, the holder of the land may not necessarily be or have rights to the water. In other words, the holder need not be the landowner to hold the water rights. The landowner may not have any rights at all, in fact. This kind of goes back historically, particularly out west where we had less water as our country changed and people moved more so westward, that this happened. The law states, in a simple sense, it's the first person to use or divert the water has the primary right. The first person to use or divert the water has the primary right. And that gets kind of technical now at this point of view as to this particular scenario. Again, whether we have this riparian doctrine or the prior appropriation doctrine, even under the prior appropriation doctrine, the user or the first to divert, they only have the primary right. They don't have complete 100% rights to that water. It's just like riparian, that the states come in, it's controlled again. You get a certain amount of it. You'll be allocated a certain amount of that water. So these are the two main ones you need to remember. All right. Now, of course, there's all these other people involved in wanting uses of the water that come into that formula, where the state says, okay, you'll get this, you'll get that, and so on. So it's domestic waters, it's the irrigation for the farming, and of course industry wants their share, and commercial wants their share. And everybody wants a piece of the pie. And so this is the legal thing of how do we divide it up. And that's where controversy comes into play, whether it's fresh or polluted. You want to know a lot about water in the state of Kansas, you can go to this www.kwo.org. That's the Kansas Water Office. It has more links again than you could think of. It takes you to many things about the legal issues of water. It's not as simple as these two. The textbook tries to simplify it. Here we have a map that kind of shows, where the surface water principles are applied in the United States. And you can see that the state's kind of eastern half of the United States, not exactly all over east of the Mississippi, but generally to that half of the country where there's more rain, more lakes, more reservoirs, more water available, and where we started. As the country changed and populated, moved westward, you'll notice that it's mostly what? Riparian. Okay, it's mostly riparian. As you move to the western half of the United States, and this makes good questions, all these things I'm talking about here, really good questions, it's exclusively appropriation, but if you look at Kansas, it's a mixed bag. It's both riparian and prior appropriation in there. That's surface water. Now groundwater adds another kind of dimension here, same kind of map. You look at the eastern, generally the eastern half of the country is what? Riparian. Generally the western half for groundwater is what? Prior appropriation in this case. Again, Kansas is prior appropriation for groundwater. But we've got a couple other situations in here that are different. Something called reasonable use, that they're kind of changing some of the older laws, and several states have adopted some new types of scenarios. One called reasonable use, and the other one called correlative rights. Now, I'm not going to go into the long, lengthy detail of what these are, but you notice California is one. What's that little state over there? New Jersey, okay? And then for at least the correlative rights. Kind of interesting stuff. So, what do you have to think about when you slice up the pie? I'm going to just show you a bunch of pictures. We'll go through things. You don't have to go through a lot on this. But the first picture I show you in terms of slicing up the pie, first starts out with, how much water have you got? Someone's got to figure out, how much do you get? Well, that's precipitation, right? Water, snow, sleet, doesn't matter. And this water comes down and hits the surface of your place. This happens to be the Kansas's water budget kind of diagram of these pieces of the variables on this stuff. Well, when you do that, the water usages, some of it's going to go into the groundwater system, right? A certain amount of precipitation soaks in the ground, a certain amount runs off, a certain amount we'll have in streams. Some we may do what to? Dam up the rivers and put into reservoirs. Other stuff may flow out of your state, or other stuff may flow into your state. It's all part of a numbers game as to how much it is. All right? And so these are the considerations of what you start out with. How much do I have? Like your bank account. You know, how much can I spend? Well, what kind of rights are out there? Eastern Kansas, most of the red, that's surface water situations. You get out to western Kansas, it's what? It's more groundwater scenarios. So how do you slice the pie? Well, that depends. Eastern Kansas gets more rain. Western Kansas doesn't. So precipitation rates come into play. You don't have to memorize these numbers at all. How much runs off of your state? So you can retain it. If it's running somewhere, where's it going? Is it going across this drainage basin into this one? Is it part of Big Creek? Is it part of the Arkansas River? Is it part of the Saline River? What drainage basin or watershed does it belong to? So first you have to define your geography and figure out where the water flows to across this area to another one. And when it does that, in what river systems, which ones we've dammed up, which ones flow into our state from another state, which go out to another state. How much is in your reservoir now? Somebody's got to monitor that. Then we say, okay, let's create districts, water districts, as to who's going to have certain scenarios in these zones. These are all maps you can get off the Kansas Water Office site. Tremendous amount. Then we'll get into intensive groundwater uses. Who's using it the most, and where, where's the recharge part to get that part of the groundwater system fixed? And so all these things have come into play. The IGUCA, the Intensive Groundwater Use Control Areas. It's a group of people who make up the rules and monitor this and have to report. And the underground water, the big one, it's not just Kansas, our High Plains Aquifer. It's the whole part of the High Plains, from the Dakotas down to Texas. It's that Ogallala, isn't it? So the intensive work being done on the Ogallala is absolutely amazing that we can find out just in our state. It's not just Kansas. Nebraska and these other states all do the same thing. Natural recharge. All right, how much is going there? Well, how much was there before we really developed our country and started pulling it out? The maps for that. Well, what happened after we pulled it out? What's the storage capacity? How has that changed? And given that, how much do we say you can have? You get so much a cup here. It's like you're out hiking and you get, you want to say you get so much water to drink to last a week. So there's a lot involved, okay? So obviously we've got the pollutants, we got the games we do to clean it up, we've got this and that. And then we say, okay, now we have to fight over it, don't we? And this is where the lawyers come in. This is litigation, all right? Write down table 10.4. We have probably another 10 minutes, folks, so hang in there. This is the longest lecture I told you we would have. Kind of bear with it, okay? Be sure you look at table 10.4. It lists a lot of international problems of who's fighting who over what water. And it's going to get worse. World population's going up. I don't have time to take you to this website, www.uswaternews.com. If you go up to that, uswaternews.com. You don't have to list the rights of it. But boy, it's amazing to go to this website and see what's going on with this. Check it out. Go to their archives and look at things on rights and who's doing what to who. I'm going to throw you a few examples real quick. We're getting close to the end. Arkansas River Project in Colorado is a big thing. Kansas has been suing water over the Arkansas River water rights. They call it the Arkansas River through Colorado. Here in Kansas, called the Arkansas River. And you can get onto a Colorado site, see how they're divvying it up, and then what goes across the border. Now, the Supreme Court said Kansas won. Now, they're trying to do that. Nebraska, Kansas, Colorado, we're all looking at our water issues, debating the pros and cons. The lawyers are involved, the ranchers are involved, the communities are involved. The United States and Mexico over the Colorado River. Here's kind of our desert southwest. This is Southern California, the Salton Sea, that little body of water. The blue is the Colorado River. The populations have gone sky high out there. We divert water out of the Colorado River to lots of places. Here's the next view from space. Here's that Colorado River coming along here. Here's Mexico, the United States. Salton Sea, Gulf of California, this is where the Colorado River Delta in the Gulf of California. All right, well, the Salton Sea wasn't there at one time. Something happened. We were building little diversion canals on the Colorado River. 1906, the quality of these things weren't too hot, they broke. A lot of too much water, they broke through the levees and these canals, and they went to the low spot. Well, the low spot was in Southern California after they broke, and that just for a year it kept filling in and flooding in and created this great big lake, the Salton Sea. All right, and they got it fixed, got it back on track. Here's a shot of Yuma, Arizona. I just passed through here a little while ago. Here's California one side, Arizona here, Colorado River. You can see this nice canal. Canal after canal after canal going off. Yuma, Arizona, the Imperial Valley. Lots of food you eat comes from there. Lots of fruits and vegetables. Mexico does the same thing, but they want more water. The quality water we send them had gotten a little too salty. Look at all these wonderful plants. We build a community. We put up all kinds of plants because it's pretty. Now, they certainly conserve water a lot more and better down there than we do. And then we do better than somebody else further east. They have more water. So it's kind of like the movie Dune. Remember that series about the need for water and all the still suits and recycling. It's a precious commodity. As you go into California, you go across another great big canal, the Great American Canal. It's on its way to Los Angeles. They have pumping stations. They pump it over mountain ranges and take it over there. San Diego, that's where they get a lot of their water. Colorado River. That's why it doesn't go to Mexico. They're not happy about it. Here's where it broke. Some really old pictures, just flooding through these gates. Great big lakes filled up. They even set up resorts and had bars, this thing called Captain Mullet's. People go fishing. Had a great time there for a while. And they finally got it back on track. So we've come to some kind of common ground with Mexico. They say it's fixed. It's not 100% fixed. It's partially fixed. Some things resulted from it. Scenarios. There have been some industries. I know that a lot of the clams, notice these clams down here in the bottom. A lot of these things are bulldozed around, and they all were down there, got killed off, but then they got them for shells. They didn't get the food out of it, but they bulldozed the shells, and you can see people, they take buckets out, and so we have all these shell farmers down in this delta system down here, and they're making money off it. They use it for various things, and it's interesting. So, we've covered a lot on water. And just to culminate this, again, I just want to tell you that water is the most important thing we've got. Without it, we have nothing else. It's happened in historical past and archaeological past. It can happen in the future. And so we have decisions to make about a lot of things that we have, how we deal with our neighbors, and that list goes on and on. But if anything you learn in this course, the last 3 chapters, don't forget. All right? That's it for today. And we'll wrap up this one more with next week's lecture on, unfortunately called The Great Dyings, not to kind of look at the future. So we'll see you then.